All right, let's keep going. All right, so the test that we just took was on the very first part of two-dimensional motion. All right, so remember we broke two-dimensional motion down into two different parts. The first part was vectors. The second part, which we're going to start today, is projectiles. All right, so with vectors, all right, so we had arrows. That's what we were just looking at, a lot of arrows. We were able to add those vectors together. We were able to find the magnitude of those arrows. All right, both mathematically and graphically. And then we found the direction, both mathematically and graphically, whenever we're talking about angles. All right, we learned about counterclockwise direction. We learned about cardinal direction, all of that good stuff. All right, so today we are going to continue with two-dimensional motion. So the one thing that I really want you to take from vectors is that because they were at some angle, they had both a horizontal component and a vertical component. That's what made it two-dimensional. All right, so what we are looking at with projectiles, the reason that they are different, you can see in this picture, all right, we have something that has been launched into the sky. All right, with vectors, we would have just looked at this one part. We would have just looked at that one vertical and one horizontal part of it. But with projectiles, we can see that it keeps going past that arrow. All right, it's actually going to create a curve. All right, and that is called projectile motion. All right, so that's what we are going to be talking about today. Now, projectiles itself is broken down into three different parts. We're going to be talking about three different things with projectiles. So not only are we really introducing what projectiles are, we're also going to be focusing on projectiles that have been launched horizontally. All right, so this is what your quiz is going to be on. This is what the vast majority of your test is going to be on. This is where the main math comes from. All right, so this is super important. All right, so what you need to know as we are starting is that a projectile is any object that is launched into the air or dropped that accelerates vertically due to gravity. All right, so we know that we have a basketball. It's basketball season, so we can shoot a basketball. All right, that, say you're going for a free throw, that motion of the ball is projectile motion. As soon as you throw it, it becomes a projectile. A gun, whenever you shoot a gun, that bullet becomes a projectile. If you're hunting and you're shooting with a bow and arrow, that arrow becomes a projectile. We have tennis, all right? If you're hitting a baseball, a tennis ball, a golf ball, anything like that, then those are going to become projectiles as soon as they are hit. All right, so projectile motion is how we described the curved path of an object. All right, so if we were on a place that did not have gravity, then this water spout would just keep going on and on in the same direction without changing its course. It would just keep going. But because we do have gravity, it creates this curved path. Now, in math, we call this shape a parabola. All right, and that is what projectile motion looks like. All right, so projectile motion, sorry, I can't talk and write at the same time. Projectile motion is parabolic motion. Okay, so projectile motion will always take that parabolic trajectory, that parabolic shape. All right, so before we really get into these parabolas, these projectiles, I do want to review what free fall is. All right, so free fall motion occurs whenever you have something that is traveling through the air near Earth's surface. Now, we dealt a lot with it with things that were falling, but remember, it was for things that were falling and things that were thrown upward. All right, so I'm just going to go down here. All right, so if we have a ball that has been thrown upward, again, this is just a review. All right, then its velocity's direction is positive, but we know that it has acceleration due to gravity, which is always that negative 9.81. All right, well, we know whenever we have a positive velocity and a negative acceleration, those are opposite signs. So that tells us that this ball would slow down as it went up. All right, and then at the very top of the motion, for that one split second, it's going to stop. So it actually has no velocity, but because it is still in the air, it's still being worked on by gravity. So it still has that negative acceleration, all right, due to gravity. And it's that acceleration that causes it to change direction and go down. All right, well, as it's traveling downward, its velocity is now negative because it's going down, and the acceleration is still negative. So we have like signs here. So that tells me that it is going to speed up as it falls. All right, so we have this free fall motion. It's not only whenever something is falling, thank you, not just whenever something is falling, but also as it is going up and down. All right, so that's what we're going to look at over here. All right, first thing I want you to do is I want you to look at this left part of the picture. All right, what we have is an object that has been dropped. So you notice that these vertical arrows get a little bit larger every time. So that tells us that this object is speeding up as it goes down. So this object is in free fall. Okay, that's what happens whenever an object is in free fall. All right, now if we look at this object right here, all right, notice that this object has been launched horizontally. All right, this is what it will look like if you have something that has been launched horizontally. All right, again, this is what we're going to be focusing on for our quiz this week. This is what's going to be the vast majority of your tests next week. All right, so very, very important that we understand what's happening here. All right, now, whenever we have something that is launched horizontally, if you notice, we're not looking at the whole parabola here. All right, all we are looking at is the second half of that parabola. So we're starting at the top and looking at that second half. All right, so that's what we are seeing. We're going to get into the whole parabola later. All right, but if we look at this ball as it travels, just look at the vertical components. All right, if we compare these vertical components with each other, all right, we should see that they are the same. All right, the vertical components for an object in free fall and an object that has been launched horizontally are the exact same. The only difference between the object that is launched horizontally is that it now has a horizontal component to it. All right, but look at these horizontal components. All right, they are not changing in size. They are not changing in direction. All right, so that horizontal component, that horizontal velocity is staying constant. All right, it is not changing. All right, the vertical velocity is, but the horizontal component is not. All right, now we're going to see this again later, but I really, really, really want you to just focus on this. All projectile motion is just free fall motion where we have added a horizontal component to it. All right, so it now has that horizontal component. All right, so the next thing that I really want you to focus on is this word right here. I hate that it's on two lines. All right, it is the word trajectory. You're going to hear us use that word a lot. All right, and the trajectory of something is just the path. All right, so a projectile will always have a parabolic trajectory. That just means that it's always going to follow a parabolic path. All right, it's always going to look like a parabola. All right, this next one, we're going to look at three different motions. If you were to pull this up on your laptop and you open it as a PowerPoint, this would play the graphic, all right, but it's not going to play on this. I do apologize. All right, so we're just going to draw it for ourselves. All right, the first path that we have is if we were, say we're in deep space. All right, and in deep space, we don't have a lot of gravity working on us at all. So say we just threw this object and because there was no gravity, it just kept going in the same direction, kind of like what we talked about this water spout would do. All right, because there is no gravity, it would just go in the same direction forever and ever and ever, amen. All right, so it would travel at that constant rate forever, all right, because there is no gravity. So this is what we're going to call a gravity-free path. All right, the second motion is going to be a downward motion. So this would be if an object dropped. Well, we know if an object dropped, it would be in free fall. All right, and what do we know things do whenever they are in free fall? We know they accelerate, they speed up. So each and every spacing would be a little bit further apart than the next one, all right? Because thanks to gravity, it's going to accelerate at negative 9.81 meters per second every single second. Now, parabolic motion actually takes from both of these. All right, it's going to have both paths. It's like if we pulled this one down and pulled this one across, it's going to give us this dot. If we pulled this one down and this one across, it's going to give us this dot. If we pulled this one down, sorry, doing my best, and we pulled this one across, it's going to give us this dot. All right, so on and so forth. We'll just do these last two real quick. Oh, I forgot to bring it over. All right, so it's going to pull it down. So what I really want you to focus on is the spacing of each. Okay, so the blue is our projectile motion. The blue is going to be our projectile motion. All right, so if you notice that the green, that horizontal motion is spaced equally throughout. All right, that's because our horizontal velocity with horizontally launched projectiles is always going to be constant. All right, horizontal velocity is constant. But if you look at our vertical motion, it is speeding up. So our vertical acceleration is the thing that's going to be constant here. Now, these do not mean the same thing, and you should be able to see that by using those lines. All right, that horizontal velocity being constant means that velocity, the horizontal velocity, is not changing. But the vertical acceleration being constant means that after this second, it would be negative 9.81. After this second, it would be double that. All right, so let's just move it to 10 to make it easier. This would be negative 10. This would be negative 20. This would be negative 30. This would be negative 40. This would be negative 50. We have seen that before. All right, so you see that these velocities are not constant, but they are constantly increasing. All right, so that's what we mean by constant acceleration. Okay, so I want you to keep that in mind as we go. Oh, no. Okay, nope, sorry. There we go. All right, so we have new-ish equations. These are not new equations. All right, these are not new equations. We have taken our kinematics equations and we have repurposed them. We have made them more specific for vertical motion. All right, and we are using these whenever we drop or launch something horizontally. So these can only be used whenever something is dropped or launched horizontally. And the reason that these can only be used then is because whenever they are dropped or launched horizontally, just like with something that's in free fall, that initial vertical velocity is 0. So whenever we were dealing with free fall, we said that if we drop something, that initial velocity is 0. It's the same exact thing. We are just specifying it to be vertical. So our vertical initial velocity is going to be 0. So if we were to take out that initial velocity in those equations, all right, because it is 0, we would get these three equations. All right, so here we have the final vertical velocity is equal to acceleration due to gravity times delta t. This comes from the second kinematics equation. All right, Vy final squared is equal to 2g times delta y. All right, that comes from our last kinematics equation. And then this one, delta y is equal to 1/2 g times delta t squared. That comes from our third equation. Again, we have taken out that Vy initial to be more specific, because it's going to be 0 whenever things have been launched horizontally. All right, and we know that if something is launched horizontally, we just said this earlier, that it has a constant horizontal velocity. So that's what you're going to see right here. We are not going to have Vx initial and Vx final like we see up here. Here we have Vy initial and Vy final. All right, we don't have that for horizontal because it is constant. All right, so we don't have Vx initial and Vx final. All we have is V sub x because it remains constant the entire time. All right, so we have this equation. This came from our original velocity equation. So we know that the horizontal velocity of objects is just equal to that horizontal displacement over time. So that was our original velocity equation. This is just it rearranged to solve for that delta x. All right, you can use either one of those. They are one and the same. All right, so let's do our first example here. All right, so suppose this ball is pushed off of this table. All right, so that means that it was launched horizontally and it's going to land on the floor. All right, the table is 0.7 meters high. All right, so that 0.75 meters high is that. All right, that's what that means. And the ball's displacement is 0.58 meters from the edge. So that means as it left the edge of the table, all right, that the horizontal displacement was 0.58 meters. It landed 0.58 meters away. All right, so those are our two given. So we have delta y of 0.75 meters and then a delta x of 0.58 meters. All right, now we know that this object has been launched horizontally, so there are two things that we know we can infer. All right, the first one is because it's falling, we know that it has acceleration due to gravity. And then we also know that its initial vertical velocity was 0. Okay, initial vertical velocity is 0. So I have asked you, how fast was it moving when it left the table? All right, so we're looking for a velocity when it left the table. So at this point, what was its velocity? All right, well, that's at the beginning. We know that its initial vertical velocity was 0. So the only other type of velocity that it could have had at the beginning was a horizontal velocity. So we are looking for horizontal velocity. All right, now we know that the only equation that we have for horizontal motion is that delta x is equal to v sub x times delta t. All right, we're solving for v sub x. We have delta x, but oh no, we do not have delta t. So we have to think back to that, what words are hard. My brain is not braining right now. Relative velocity. Yay, I figured it out. All right, so we have to think back of when we did relative velocity. I told you that whenever we're dealing with these vertical and horizontal components, they act independently of each other. All right, so horizontal only affects horizontal, vertical only affects vertical, but the variable that connects them both is time. All right, so that tells us that we can use one of these equations to solve for time and then plug that time into this equation to solve for our horizontal velocity. All right, so let's go up here. Let's look at these. All right, so Vy final is equal to G times delta T. Well, we're solving for delta T. We know G, but we don't have our final velocity. The second one doesn't even have delta T in it. So the only one that we could use is the third one. Let's see if we can use it. All right, so we're solving for delta T. We have G. Oh, and look, we have delta Y. So let's use that last one. All right, so let's go back down here. So that's going to be delta Y is equal to 1/2 G times delta T squared. And we're going to solve delta T. All right, so we know that we have to get delta T by itself. So we're going to multiply both sides by 2 first. All right, so that's going to get rid of that 1/2. So that's going to be 2 times delta Y is equal to G times delta T squared. We're going to divide both sides by G now. And then to get rid of that square, we're going to square root both sides. So that leaves us with delta T is equal to 2 times delta Y over G. All right, so that means that we have 2 times I don't know why I did that. 2 times 0.75 divided by 9.81. Remember that we cannot put a negative under a radical. So we plug that into our calculator. We should get 0.391 seconds. All right, now that's not our answer. That's just going to help us get our answer. So we can plug that back into that original equation. All right, so we have, What's happening right now? Okay, there we go. Okay. All right, so we have our original equation. I'm just going to bring this down here. So we have delta x is equal to v sub x times delta t. Solving for v sub x, we're going to divide both sides by delta t. So our horizontal velocity is equal to our displacement over time. So that's going to be 0.58 divided by 0.391. All right, I'm going to pull this down here. I'll erase it before we do this next example. All right, so we divide those out. We should get about 1.48. 1.48. Now, this is a velocity, so that means that our unit is meters per second, and velocity is a vector quantity, so we have to add that direction. So I didn't give you a direction, so we're just going to assume that it's going in the positive. So we know that as this ball left the table, it had a horizontal velocity of 1.48 meters per second. At this point right here, its horizontal velocity was 1.48 meters per second. Right here, it had a horizontal velocity of 1.48 meters per second. And then that split second right before it hit the ground, its horizontal velocity was 1.48 meters per second. All right, so that's what that tells us. All right, and remember that it's just V sub x. It's not Vx initial and Vx final. It's just V sub x. All right, so let's do this example. We have the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. It is terrifying. All right, suppose you kick a rock horizontally off of the bridge. The magnitude of the rock's horizontal displacement is 45 meters. Find the speed at which the rock was kicked. All right, so we know that we were up on this bridge and we kicked this rock off the bridge, all right, and it fell into the water. All right, so we have another horizontally launched projectile. Okay, so we need to keep that in mind as we are solving this. All right, so our first given was this 321 meters above the river. So that tells us our vertical displacement that the rock would have fallen. All right, so that's 321 meters. All right, we also were told that its horizontal displacement was 45 meters away from the bridge. Again, we know it's horizontally launched, so that means that our Vy initial is 0. Our initial vertical velocity is 0. And we know that as it is falling, it has an acceleration of negative 9.81. All right, so those are all of our givens. Now we look at what our unknown is. It says, find the speed at which the rock was kicked. Well, it was kicked up here on the bridge. So that's at the beginning. So we're looking for a velocity at the beginning. Well, we know that Vy initial, the initial vertical velocity, was 0. So again, the only other type of velocity that it would have had at the beginning is that horizontal velocity. So just like the one that we just solved, we're solving for horizontal velocity again. Okay, so we know that we can only use that one equation, delta x over delta t, to solve for our velocity, our horizontal velocity. Again, we have delta x, but we do not have delta t. So we have to solve for delta t using the exact same equation. So I'm just going to go ahead and rearrange it just for time's sake. So we know that delta t is equal to 2 times delta y over g. So that's going to be 2 times 321 divided by 9.81. That's going to give us 8.08971 seconds. Now notice that I went to several decimal places. Because this is not a final answer and we are actually using this answer to get another answer, I do usually go a few more decimal places. All right, so now that we have our time, we can substitute that into this original equation. So we can bring that back up here. So we know that our horizontal velocity is equal to our horizontal displacement over our time. All right, 0.971. We divide those out and we should get 5.56. Now this 5.56, it is a velocity, so it's meters per second. And velocity is a vector quantity, so we add that direction to it. Now, whenever we do more practice, these were the same, all right? I was looking for a horizontal component, so I had to use vertical components to find time. Well, I could have done it the opposite way. I could have found time using the horizontal components and then subbed that in for a vertical equation. All right, so it works both ways because it's actually happening at the same time. Your horizontal component is happening at the same time as your vertical component. All right, so time is what connects them. All right, this is kind of what we saw earlier. It says, suppose a rescue pilot drops a relief package while it's moving with a constant horizontal velocity at some elevated height, assuming that air resistance is negligible. That means that we are not including air resistance in this scenario. It says, where will the relief package land relative to the plane? So this, again, just like up here, all right, this package does not fall straight down. All right, you should have seen that in this up here. All right, the package does not fall straight down whenever it is dropped. All right, because it is in that plane, it has that horizontal velocity. It has the same horizontal velocity as the plane does. So as it falls, it's going to fall. Oh, that's not good. It's going to fall. We know that it's going to speed up as it falls, but the horizontal velocity is going to be the same. All right, so as this plane travels this way, our box or our care package is also going to travel at that same rate horizontally. All right, so if we were to look at this, that tells us if we did not include air resistance, that package would fall right below the plane, all right, directly below the plane. Now, if we took air resistance into account, it does cause something called drag. Oh, I don't know what happened there. All right, it does cause something called drag. So in real life, because we know there is air resistance, all right, it would fall here. All right, but whenever we consider air resistance to be negligible, it's going to fall at point B. All right, it will never fall at point C or land at point C if it has just been dropped. All right, so it will either be A or B. A is real life because of air resistance. B is whenever we do not take air resistance into account. Okay? All right, well, I hope this has been okay for you. As always, if you have any questions, you know where to find me.